Welcome back to Balvik and Bharti with your own mentor Avilash Sarkar. In the last episodes, we have discussed about the application regarding your Bernoulli's theorem. Two of the applications are venturimeter and the next one is Torricelli's law. There we have learned the speed of efflux, and there is a two condition of speed of efflux. One is open reservoir or tank, another one is closed reservoir on the or the tank. In the latter case that we have learned, instead of atmospheric pressure, that is being governed by the vapor pressure, and regardingly what is the effect on the speed of efflux that we have learned, and regarding some more topics we have learned. Now that was the end of the fluid dynamics, where we have taken the consideration of ideal fluid. So the ideal fluid, as I said, it has having three properties. It is incompressible, second one is irrotational, and third one is non-viscous. So this was the three conditions on which we said we are talking about ideal fluid. Okay, I am repeating every time because so that it will be a recapitulation of the earlier subjects that I have taught, and you can get a bridge upon the next subject. So this is ideal fluid. Now we'll move on to the non-ideal fluid. Now this case our next topic. In next topic, our fluid will be is non-ideal. So if I say non-ideal, is that mean that all the part are deviated? Yes, we can have all the criteria being deviated. It could be incompressible, from incompressible to compressible, irrotational to rotational, non-viscous to viscous. But the out of the non-ideal cases where the fluid could be the non-ideal fluid with combination of any of these three being deviated. Okay, out of all three, one is deviated, all three deviated, two deviated, and combination of that. Out of that, our case is Newtonian fluid. So we'll confine ourselves further to only few deviation. What are those deviations? Newtonian fluid says we are keeping these two part intact. We'll only talk about Newtonian fluid, where fluid has only viscosity. So that means the fluid will have viscous property. That is fluid have viscous property. Okay, so this is our acceptance. Okay, now what are the things will add up to this? So one thing is that it is Newtonian fluid. Other things it will maintain. Other things is it will maintain laminar flow. So next part of the discussion we will take it Newtonian fluid, where these two part is still exist. This is converted into viscous fluid, and this is having laminar flow. If these two conditions matches, the third condition that will arrive is convective acceleration. Convective acceleration is 0. Now, what is this convective acceleration? Okay, now we'll focus on this. So you understand, this is our case, non-ideal fluid to ideal fluid to non-ideal fluid. In non-ideal fluid, I will only deviate this condition, the other is intact. So this will give you Newtonian fluid. Newtonian fluid, along with that, it will maintain laminar flow. So that means your Reynolds number must be less than 1000. This has to be maintained. Okay, and another term that has came is convective acceleration is 0. Now we will talk about convective acceleration. Prior to the convective acceleration, let me introduce Reynolds number again. The Reynolds number that we have discussed is having a non-dimensional. There is no dimension, all these numbers exist, and that is being calculated by rho v d h. Now I, instead of the earlier we have taught d only, now I am bringing some suffix with that dh, and I will tell you what is that. Now this is eta. Instead of eta, we can represent it as with mu also, because mu or eta are both representing dynamic viscosity. Now when you will talk about viscosity, I will learn it. So but as this term is very much related to the viscosity, it's very much essential to bring that in discussion again. So now mu, and this is called mu. These are all Greek word. This is called eta. Okay, these are, so eta and mu. In some cases in study of science, they are representing chemical industry and all that. They are representing it in with this mu. Some industrial physics and all that, they represented as eta. So both are same thing, and you know the unit of measurement is m L to the minus 1 T to the 1 minus, if SI unit if I take, it is kg per meter into second. Okay, so from there we already derived, but again I am deriving kg. If I multiplied with meter, if I multiplied with second square, and now as I brought it here, so second will be there, meter will be again there, so it will nullify, or sorry, meter square. So this will be the case. Okay, so now kg meter per second, this is acceleration, this is mass into acceleration is force Newton into second per meter square. Now again this is equal to Pascal, so this again is Pascal second, Newton or Newton meter per Newton second per meter square, or this kg meter per second. So we can see the conversion, any of the equation, any of the unit is true for your dynamic viscosity, Pascal second, Newton second per meter square, or kg meter per second. These all are valid for those. So ultimately if I break it into this, the ultimate unit will be m L to the minus 1 T to the 1 minus of the lowest combination of unit, you can say. So this is the unit. Now this is dynamic viscosity. What I am saying, this eta and mu are same, and this represents the dynamic viscosity. Now this again can be represented, this velocity into dho. Let me introduce dh. dh is the hydraulic diameter. Now let me explain it a bit. Now say the fluid is flowing through some boundary, it's a rigid boundary, this is some pipe, there is a fluid which is moving through it, and this is the hydraulic diameter of the fluid through which duct it is flowing. This is rigid, so it will take the shape of those contour or the duct through which the fluid is flowing, and the maximum if it is a circular cell, the diameter through which it is maximum diameter of the fluid through which it is flowing, it is the hydraulic diameter of the fluid. Okay. Now this hydraulic diameter, in case of fluid flowing, it depends on the state of we'll consider the state of steady state flow. So in case sometimes this may happen that it is flowing through some opening on a reservoir, the initial of this, it will take the diameter of the pipe. Then later on, this, due to the frictional force or the viscosity, it will take a bit less diameter shape, and slowly it will flow through a very you can say the narrow flow path. Okay, so this part is not the part where the flow is fully developed. So what I am talking about, the steady state flow for any case where the viscosity is being considered will stay till it is converted into the fully developed flow. So this term is very much used in describing this kind of flow where fully developed flow is established. Okay, flow is established. So this is the part, it is away from the initial stage of flow being started. So this part, it is not fully developed. The fully developed flow, where you see the cross section is very much uniformly distributed. If it is before the flow is become turbulent due to the any reason or any restriction, if it is flowing through some uniformly cross section path, so that is the fully developed part of the flow being has to be considered during this steady state flow. So when we are talking about considering non-ideal flow and the viscosity, we have to wait till the flow is developed fully. Okay, so this need not to be understood so much, but we'll take the consideration the flow is steady flow and the uniformity is same. So when it is taking the path of the flow, so this is the diameter through which the steady state flow, the circular diameter of the fluid flow path is called the hydraulic diameter. Okay, so we'll consider here the hydraulic diameter of that, or in case if it is not said anything, more or less we take it is being flowed through a closed duct, so we'll take the diameter of the duct itself is the hydraulic diameter. Okay, so this is the case. So what we can arrange this formula in another way, so that is V into D will be there, this rho will come down below this eta. So this having a separate meaning, this divided by rho, or you can say mu, is your, this is called nu. I don't know it is the right way of representing, but more or less something like that. So this is nu, this is your kinematic viscosity. Okay, this is your kinematic viscosity. Fine. So this also can be represented, now it is V into dH. Now let me take this part of this board. This is V into dH, hydraulic diameter, divided by nu. So V is the velocity, you know it, velocity. This is the hydraulic diameter, and this is kinematic viscosity. So this is the part. So this way also the Reynolds number can be represented in case the information is such that you will get these three, so we will get the Reynolds number directly. Now this can also be represented in other form. If I further change this equation, this V into, if I multiply with the cross section of the flow path, let's say this is flowing through a duct and this is having cross section of A, so A into V, if A I am bringing on the both numerator and denominator, so this into A. So now this will become what? Cross section into velocity. This cross section and velocity will give you the flow rate. This is flow rate into dH, hydraulic diameter, divided by nu into A. This also can be one way of representing the Reynolds number. So if flow rate is there, hydraulic diameter is there, the value of the fluid kinetic velocity and the cross section if it is known, so we can get it like that only. Okay, so these are the three mode of representing Reynolds number. Now the nu, which is eta upon rho, if I see the unit, it will become ml minus 1 t minus 1, and rho is your ml minus 3. It is mass by volume. So if I cancel it, it will become L square by T. So in SI unit, it will become meter square divided by second. Okay, now this is the unit of kinematic viscosity. Now this can also be represented, if I want to represent it, m into let's say L I am taking, then T square I am taking, so remaining will be L is extra here, so L to the power minus 2 here, T instead of T to the power minus, so this will be T again, T to the power minus 2 I have taken, so this will be T to the power minus 3, and here M L to the power minus 3, isn't it? So this will balance the equation. Now ml into T cube, the m into L, this is your in SI unit, if I say this kg meter per second square, that is equal to kg meter per second is in Newton, kg meter per second is Newton, into in SI unit, let me check it, this is will be meter down, this will be meter on the top, L to the minus 1 on top, and T to the power minus 3, kg meter, Newton meter, that means m will be there, and the m is there. Is it true? It is right. M T to the power minus 1, L is there, so ml is a Newton meter into, and T is T to the power minus 2. If I take, this will be T only, sorry, this will be T then, so sorry, this will be T, so this will be balanced, m balanced, L minus 1, so L minus 1 and L minus 3. What I have balanced here? Yes, L minus 3 is there, L into L minus 1 is coming, T to the minus 2, T is balanced. So this is again, if I take the formation, so this will be M L T to square into this will be T into M into L will be there on the top, so L will go on the top. Okay, fine. So this part is ml into T to the power minus 2 is equal to the force unit, force, this is Newton, into L into T by M. So F into L, that is equal to energy unit, so the energy into T by M. So that means this is become what? Energy per meter, that means specific energy into time span of the flow. You can consider, if I want to get the kinematic viscosity, the specific energy of the fluid into the time of through which the thing has to be considered, is this can be represented into specific energy into time by the time we have to consider the kinematic viscosity of the fluid. So we have to consider some time during which we are calculating the parameters. The parameters are the energy that being reduced, that pressure energy being reduced, the energy conservation you can say per mass per kg. So there must be some mass is flowing, and the energy from one point to another point, what is the change in energy, and by mass that will be the specific energy, and during the time this being considered, this being measured. So that time if you multiply, we will get the kinetic viscosity. So this is the practical experience by which we can get this kinematic viscosity value. So the ultimate unit of the kinematic viscosity will be m will be cancelled out, and this will be L square by T. So this will be the this is the dynamic viscosity, m L minus 1 T minus 1, and kinetic viscosity there is no mass is being involved, only meter square per time. So if we know the length of the duct, so you will get the meter means length, and by the time, if you can see from here to here how much time it is taking to travel, okay, so you will get the kinetic viscosity easily. So this is about the Reynolds number, and as you know already, the values of Reynolds number, how it has to be calculated, that I have already told. So the next comes dynamic viscosity. Okay, so we'll move into the topic dynamic viscosity. Dynamic viscosity. So in any flow where we consider viscosity, we'll talk about the dynamic viscosity. Straight we will not talk about the kinetic viscosity, because dynamic viscosity is related to the flow relations. Okay, so what is viscosity exactly? It is nothing but the frictional resistance between the layers of the fluid flowing. So this is simply can be thought of that way. It may not give you some clear picture what is that, but thing is that as any object, whether it is solid or liquid, if it is flowing over each other, that definitely some resistance will act on the opposite side of the motion. That is the force which is called the frictional force. Here in case of liquid, if it is moving on a solid surface or moving on each other, the liquid are moving, or the fluid is moving on each other, that will get some resistance to flow. That in earlier case, ideal case, we have not considered is there. So in this case, as we are talking about the viscosity, we will say there must be some resistance acting between the layers of same fluid, or the fluid and the solid surface on which it is flowing. So if I say, if it is so, now if I think about those two layer of solid parallel plane, and in between the fluid are flowing. Okay, fluid are flowing. This is at rest, and this is moving. Okay, now if this is moving, the layer just adjacent to this will get the maximum velocity due to the force it will give to the layer as it is attached to it, and it must have some means adherence to the solid surface, and it will drag it, the layer adjacent to that, it will get a dragging force with it, and the layer will get the maximum velocity as it is very means just nearer to the moving plane. So it will get some force to move with it, and the next layer that will there, it will try to, because we can think of the liquid layer layer after layer. If it is layer after, this is trying to move this forward due to the solid motion, but this will try to make it in own position, because these are contacted to each other, that is not a separate one. So as because there is some attachment to each other, adhesiveness or cohesiveness, whatever you say, between the layers, it will try to drag it back, and some elasticity will cause, because this could be the original position of any liquid element. If I take, this is the top layer, this is the bottom layer, at any point of time this point will try to move parallelly on each other if there is no there is no deviation in force, means there is no extra force acting on this and acting on, as because as we can see, if this is a solid, it is moving all its layer together, all its particle layer together, so these are very closely bound. But in liquid that is not so. If I get a more force on the top layer, it will slide down and it will cause it to move faster than the adjacent lower level, because this is not getting that much force as this is getting force. So this is getting force due to this momentum of the top layer, this is moving, and due to that it is going back. This is giving a force, this is also trying to move it forward, as because this is getting momentum, but the solid, how much momentum it is getting cannot be transmitted fully there. This will giving a force to move forward, but this is not transmitting the same force to, because this again it will maintain its inertia and it will try to give a force backward to maintain the top layer in its position. So this force which is caused by the bottom layer to the top layer is called the viscosity force. This is the force of viscosity of the frictional force basically. This is called the viscosity force, but this is basically the frictional force which is resisting the top layer to move forward, as this is insisting, the solid layer, it is insisting due to its momentum to drag the layer just added to that to move up, but this causing to move down, and at the same time this also is giving a force upward. So whatever the bottom layer is getting a force due to this, because this is getting a momentum, so this is getting some momentum due to this, upon some time this is getting a force, but this force is not equal to the force that solid is transmitting to that. This is between this liquid to liquid, so this is giving also force, but the next layer also is trying to move it back. So same way the things are going, and slowly the layers after layer the velocity is dropping. Now if I say like that, at the end if it is rest, the if we consider the layer just as adjacent to this, it will try to move by the top layer of this on the forward direction. The layer just adjacent to this rest surface is trying to move up forward with the force it is being transmitted from the top layer, but this is a rest, it will give you more force due to its inertia condition, rest condition. So it will not try, the force will of this side, it will overcome this and it will be at rest. Okay, so now if I say this is the force, the frictional force, it is causing the viscosity of the liquid, and you can understand practically, more the tensile fluid, more the density of the fluid, it will cause less tendency to flow freely. As if we can consider, also given an example, if we put a droplet of water, it will go faster with an inclination of theta, whereas if we give a droplet of honey, it will move very slowly, and that move will be somewhat like that. The top layer will come first and the second layer like that, and for water it will be a slide down. So that frictional force between the surface and the liquid that is in contact, it will be less, whereas that honey having getting more friction, so it will not move so fastly. Then that the top layer, which is with contact from the air, will get lesser frictional loss, frictional force on the top layer, and it will try to overcome the frictional force due to the air, and it will try to move faster, and this will be any go back. This will get the more force, and it will not able to move so fast. So this will give you a rolling motion. So more the density, will be lesser will be the lesser will be this velocity, means the velocity of the layer which is moving with contact with the moving surface. Okay, so that means I mean to say, for the fluid which is having density will not get much velocity with the moving part, it will slow down easily. Okay, so but in case of, if I consider the water as the best Newtonian fluid, which will maintain all these assumptions correct, and it will follow the path accordingly that I am describing. Okay, so I mean to say, so the velocity profile, if I say that the nearer to the moving plane, the velocity will be highest, and velocity at the rest will be 0. So if I take the velocity profile, it will be something like a curvature with the distance from the reference. If I take this is the reference, the rest, it will get like that. And similarly, the profile of the frictional force, that will be less here, almost 0 you can say, and from there at the bottom it will be something, a linear curve will come, where the value of the frictional force will go on increasing much you move towards the plane which is at rest. So the curve will, from this direction, if I say the distance is increasing, with the distance the velocity will increase towards the moving plane, and the frictional force will decrease as you move from the rest to the moving plane. So this will be the curve. So this will be somewhat parabolic, that I will establish, and I will understand how it is parabolic, and this is linear. This also I will explain how it is linear. So this linearity will be on the basis of the direction. Okay, direction from the rest to the moving plane, and this is just reverse. The velocity will go on increasing as we move from the rest to moving plane, and the shear force, or the viscosity force will go on decreasing as you move from the rest to the moving plane. So this will be the flow, you can say the flow diagram for a laminar flow with viscosity with a Newtonian flow. Okay, so here I will stop my lecture today. In the next video I will move on this, and I will establish some of the relations that will help you to do some numerical problems later on. Okay, so thank you for now.